We live in a world where we believe the underlying mechanics of reality are observable, testable, and explainable. Yet beneath this certainty lies a profound question: why does nature follow rules at all? Why is reality not a churning soup of chaos, devoid of patterns? Today, we dive deep into a cornerstone of physics, the reason these rules exist in the first place. We will explore the hidden symmetries that shape particles and the mathematical structures that seem to govern everything. This is where cosmic order begins. Simply knowing what the rules are is not enough. The true challenge is understanding why they remain valid across the vastness of space and time. Imagine dropping a ball in New York and then dropping the same ball on the moon. You expect them to behave in a predictable way, and they do. This is because the fundamental laws of physics do not depend on your location. They remain constant in every corner of the universe, from the tip of your pen to the center of a distant galaxy. This concept is known as the principle of invariance. It reveals that reality is not a patchwork of local quirks but a consistent and intricate tapestry. This consistency exists because the universe has no preferred position or moment in time. Whether you move your experiment, change its orientation, or repeat it at a different moment, you will obtain the same results. Whether you are measuring the charge of an electron, the energy of a photon, or the gravitational pull on an apple, the same equations apply. This symmetry is the very foundation of cosmic uniformity. If physics were not constant, the universe would appear random. Galaxies might form in one region only to fall apart in another, shattering the patterns we use to understand our place in existence. We test this invariance every day. In particle accelerators, we collide protons at high energies, and the same interactions occur regardless of where the accelerator is located. Every telescope and every instrument agrees: we live in a universe that follows a single set of rules. Einstein's theory of relativity is rooted in this very idea, insisting that the laws of physics, including the constant speed of light, must appear the same to all observers. This principle sparked a revolution, merging space and time into a dynamic fabric and reimagining gravity as geometry, all because the laws remain invariant under motion. Symmetry is the secret code that allows everything from electrons to galaxies to make sense. In physics, symmetry means that a system remains unchanged under a certain transformation, such as shifting its position, rotating it, or even swapping matter for antimatter. This leads us to one of the most beautiful insights in theoretical physics, Noether's theorem. Developed by the brilliant mathematician Emmy Noether, this theorem proves that every symmetry in nature corresponds to a fundamental conservation law. Because the laws of physics do not change over time, energy is conserved. Because they do not change across space, momentum is conserved. And because they remain the same regardless of rotation, angular momentum is conserved. These are not just useful observations, they are rigorous mathematical truths that explain where our laws come from. However, the story becomes even more interesting when symmetry is broken. Much of the structure in our world arises from broken symmetries. In the early universe, the fundamental forces may have been unified as one, but as the cosmos cooled, this unity shattered into the four distinct interactions we see today. This is similar to a perfect snowflake melting into a new, more stable form. The Higgs mechanism, which gives particles like electrons and quarks their mass, is the result of a spontaneous symmetry breaking. Without these breaks in the perfect order of the early universe, the complexity of atoms, stars, and life as we know it would not exist. Emmy Noether's work is the invisible scaffolding upon which modern physics is built. It tells us that our models are not just local snapshots, but global truths. It suggests that even an alien civilization billions of light-years away would measure gravity, electrons, and photons in the exact same way we do. Even if they have different names for their tools and their biology is entirely different, their atoms follow the same rules as ours. This cosmic consistency gives science its meaning. We are not just collecting local anecdotes, we are deciphering a universal language. As we look toward the edge of the observable universe, we do so with the confidence that the stars shine and electrons dance according to a harmony that is constant, elegant, and absolute. Emmy Noether's contributions are now recognized as one of the most significant milestones in the history of physics, with Einstein himself describing her work as a monument of mathematical thought. At first glance, our world seems to be made of planets, particles, and stars. But if you peel back the surface, you find a completely different landscape. Invisible fields stretch and ripple through space, controlling every force you have ever felt. Gravity pulls you toward the earth, magnetism turns a compass, and electricity powers our machines. Behind them all are gauge fields. These are not just background settings, they are the invisible scaffolding of reality, the mathematical structures that determine how particles behave and why the universe remains orderly. A gauge field is defined by symmetry, not a symmetry of shape, but a symmetry of rules. Imagine designing a game where players can wear any color they choose without affecting the outcome. This freedom to choose is like a gauge symmetry. In physics, it means you can change the phase or orientation of a field at every single point in space, and the physical results remain the same. To maintain this freedom, the laws of nature are forced to introduce a gauge field to compensate for these changes. Electromagnetism is the most famous example. In quantum electrodynamics, the electromagnetic force arises from a specific gauge symmetry. The mathematical requirement for this symmetry to hold locally is what forces photons into existence. Forces, therefore, are not just added onto the universe, they are necessitated by symmetry. All fundamental forces, the weak interaction, the strong interaction, and electromagnetism emerge from these underlying symmetries. We often measure our world in meters, seconds, and kilograms, but these are human conventions based on the size of our planet or the speed of its rotation. If we strip away these social agreements, what remains of the original language of the universe? This brings us to Planck units. In the late 19th century, Max Planck proposed a system of measurement based entirely on fundamental constants, the speed of light, the Planck constant, and the gravitational constant. These units do not depend on any human artifact. For instance, the Planck length is unimaginably small, a point where the very meaning of space begins to dissolve into a quantum foam. Similarly, the Planck time is the shortest meaningful interval of duration. These constants are the underlying parameters of the cosmic stage, the operating system of reality. An alien civilization might not use inches or centimeters, but they would certainly recognize the Planck scale because it relies only on how the universe works. Among these constants, the speed of light stands as the absolute limit. In a vacuum, nothing can travel faster than roughly 300,000 kilometers per second. This is more than just a speed limit for light, it is a fundamental property of the geometry of space-time. According to special relativity, as an object approaches this limit, time slows down and mass increases, making it infinitely costly to go any faster. Light travels at this speed only because its particles have no mass. This limit also protects the law of causality, ensuring that an effect never precedes its cause. If information could travel faster than light, the logical sequence of the universe would unravel. Finally, we must consider the fine-tuning of our universe. Imagine a control panel with 19 knobs, each precisely set to a specific value. These represent the free parameters of the standard model, the masses of quarks and leptons, and the strengths of the fundamental forces. We do not yet know why these knobs are set to these specific positions. If the strong force were slightly weaker, protons would not hold together. If electromagnetism were slightly stronger, chemistry would collapse. These values are not derived from theory, they are inputs we must measure. This raises a deep mystery. Why does the universe have these exact structures? Are they truly fundamental, or are they the low-energy echoes of a much grander, unified symmetry that we have yet to discover? While we search for these answers, the consistency of these rules allows us to look at the edge of the observable universe and trust that the same physics governs the furthest stars and the smallest particles alike. The scale of existence seems to lean toward a specific balance, a master ruler that determines the mass of every particle. Why is it set so that an electron has mass, yet light remains unburdened and free? We have no definitive answer. The mixing angles of particles dictate how they shift their identities under the weak interaction, where neutrinos change their passports in mid-flight, a rule that is as effective as it is bizarre. When we plug these parameters back into our equations, the standard model achieves a precision that reaches more than 10 decimal places. It is like tuning a piano to perfect pitch in the middle of a raging hurricane. But where does this exquisite melody come from? One perspective suggests there is no reason, these values are simply brute facts of nature. Yet, most physicists are not satisfied with this. We crave a first principle, a deeper theory, like string theory or a grand unified theory, that can predict these values and reduce this apparent randomness. Some theories propose a more unsettling possibility, a vast landscape of infinite alternative universes, each with its own set of parameters. In some, the electron is too heavy for atoms to form, in others, stars never ignite. We find ourselves in this specific universe simply because it is the one where life is possible. This is the anthropic principle. Instead of asking why the dials are set here, we ask why they happen to allow for our existence. It feels like a surrender, yet it may be the reality we live in. We also see running constants, values that shift with energy levels, hinting that if we look far enough into the high-energy heart of the early universe, the four fundamental forces might converge into one. Deep within the fabric of quantum physics and electromagnetism, there is a recurring number that governs the very strength of the electromagnetic force. It is not an integer or a simple fraction, but it rules the interaction between light and matter. Most physicists call it alpha, or the fine structure constant. It is one of the most mysterious numbers in all of science. We know how to measure it with staggering precision, and we know how it affects the world, but we have no idea why it takes the value it does, roughly 1/137. Alpha is a dimensionless constant, meaning it has no units. It is as pure as pi. This is significant because it is universal. If we were to meet an alien civilization tomorrow, their physics would contain the same alpha, regardless of their measurement systems. It controls the intensity of electromagnetic interactions, deciding how charged particles attract or repel and how electrons leap between energy levels within an atom. Without alpha, chemistry would fail, matter would no longer communicate with light, and everything built of atoms would collapse. Since its discovery, this number has haunted the minds of the greatest physicists. Richard Feynman once remarked that all good theoretical physicists have this number written on their walls, worrying about it. Despite decades of effort, no one has been able to derive its exact value from pure mathematics or deeper symmetries. Some wonder if alpha changes over vast reaches of time or space. Scientists look at the light from quasars billions of light-years away, searching for any slight shift in this constant in the ancient past. So far, the evidence remains inconclusive. The mystery of alpha is part of a larger puzzle. Our reality is defined by constants that are fundamental yet seemingly arbitrary. Alpha is particularly strange because it binds together quantum mechanics, electromagnetism, and relativity, yet resists all attempts at explanation. It stands as a reminder that while we have mastered the rules of the game, we are still searching for the reason the game was designed this way. That concludes our journey into the fundamental constants of our universe. I hope these thoughts accompany you into a peaceful dream and inspire a wonderful day ahead. Thank you for listening, and we will see you in the next episode.